we are discussing the topic of phase transformation, and one of the important concepts in phase transformation is nucleation. So, today we will discuss this idea of nucleation. We have looked at phase transformation. So, phase transformation essentially involves formation of a new phase in a pre-existing phase. So, some pre-existing phase is present. Let us say we have liquid, and in this liquid is going to solidify. So, if we are taking the example of liquid to solid phase transformation, which we call solidification. So, let us take this transformation as an example, because this is a familiar transformation. Now, so in if liquid is going to solidify or form solid, a solid region has to first form. This first formation of a new phase is called nucleation. So, phase transformation is divided into two stages, a stage called nucleation followed by another stage called growth. So, the first formation of a new phase is called nucleation. So, nucleation is of a new phase. So, this region which has formed in the beginning, this is what is called a nucleus. So, this stage is nucleation. After that, this nucleus which has formed will continue to increase in size. So, the subsequent increase in size is called growth. So, growth is the size of the nucleus. So, let us look at nucleation in a little bit more detail. So, one important thing which we want to ask, that what is the size of the nucleus? The question we want to raise is what is the size of the nucleus? How large or how small can nucleus be? So, let us say, so let us analyze the energetics of nucleation process, how the energy of the system is changing if, let us say, a solid ball of radius r this is solid forms inside an unstable liquid. So, this is our model nucleus. So, a solid ball of radius r nucleates in a liquid. So, what will be the changes in energies? So, let us say we have defined, let us define G s as, let us say, Gibbs free energy free energy per unit volume of solid, and let us say G L similar quantity for liquid. So, it is Gibbs per unit volume of liquid. And let us for simplicity assume that there is no density change, that is density of liquid is equal to density of solid. So, we assume this assumption is not essential, but it will keep the mathematical development simpler. So, we assume this for the moment, density of solid is equal to density of liquid, or in other words there is no volume change. There is no volume change on transformation. So, in this case we can see that there is a free energy change on solidification. So, let us try to write that free energy change. So, let me call delta G f is the free energy of free energy change due to formation of a solid ball of radius r in a liquid, and let us try to write this free energy change. So, we have this solid ball of radius r in our liquid, and we are trying to write the expression for free energy change. So, since you can see that a ball of radius r, solid of ball of radius r has formed. So, you have 4 by 3 pi r cube times Gs is the free energy which has been added to the system, but the same volume times GL free energy has been subtracted from the system because so much of liquid disappeared. So, if the liquid free energy per unit volume is GL, then 4 by 3 pi r cube GL free energy reduction has taken place because now we do not have that much of liquid and corresponding amount of solid has been added. So, this is the change in free energy per unit volume due to the formation of a solid of ball of radius r in terms of the quantities which we have defined. And what is the sign of this? If we say that liquid is unstable, remember, so that is if we say that the temperature is below Tm, if temperature is below Tm, remember the free energies we had drawn. So, this will be liquid and this will be solid. The intersection point defines the melting point and below the melting point solid is the stable phase. So, solid is stable here. So, if temperature is below Tm, if you are working here, then liquid has higher free energy, GL is higher, GS is less. So, this term is negative. So, GS minus GL is negative. So, there is a reduction in free energy, and so this will show that for whatever the radius of radius r may be, since Gs minus GL is negative, delta Gf will always be negative. So, a transformation is possible irrespective of whatever the radius r we consider. But in reality this is not true, because we know that it is possible to undercool liquid and to keep it in a metastable form, which shows that the nucleation of solid in some cases is difficult, which means something is obstructing the nucleation to happen. And what is that obstruction? So, this is not the complete free energy change on the formation, we have to add one more term. And what is that term? Let us see, you cannot create a ball of radius r unless and until you also create what is called a solid liquid interface. So, a solid liquid, as soon as a ball of radius r of solid is formed, a solid liquid interface is also created, and a solid liquid interface will have an energy associated with it. So, that energy is called the surface energy, and we have met this in the defects chapter. So, there will be a surface energy, and let us call gamma as energy per unit area of the solid liquid interface. And this will always be positive, and this positive term has to be added to this expression to complete it. So, let us add that. You can see that for a ball of radius r, the area will be 4 pi r square, and since we are seeing that gamma is energy per unit area, so we simply multiply this with gamma to give us an additional term, and this additional term by its very nature you can see is positive. So, this will show that depending on the value of gamma and Gs and Gl, it is not guaranteed that delta Gf will be negative whatever the value of R is. So, let us try to see how free energy varies if we once we have taken into account this surface energy. So, let us draw these energy terms as a function of radius r. So, let us first draw the free energy, the volume term. So, that is 4 by 3 pi r cube Gs minus Gl, it is negative and it varies as r cube. So, it will be going down like this. And if we add the surface energy term to this, so the surface energy varies as 4 pi r square gamma. So, this will be positive and this will be going up. And if we add these two terms, then you can see that initially for a small r, r square term is dominant, but for large r, r cube becomes dominant. So, initially the curve will follow r square curve and will be going up, but gradually as the radius becomes large, the curve will be pulled down, which means you will have. So, this is total delta Gf 4 by 3 pi r cube Gs minus Gl pi r square gamma. So, you can see here now that this curve goes through, since initially it was increasing because of the r square term, and then gradually it starts decreasing. So, there is a radius, let us call that critical radius, at which delta Gf is maximum. Now, what is the significance of this radius r star? We can see if r is less than r star and we want to increase the size of the solid ball, then delta Gf increases. So, this is thermodynamically not a favorable situation, that the free energy change increases with increasing radius. So, solid balls of radius r will not grow. So, solid balls of radius r less than r star will not grow. But if you have solid balls of radius r larger than r star, then further increase in radius brings the free energy down. So, growth will be possible if radius is larger than r star. So, let us make a note of this observation, that for R less than R star, delta GF increases as R increases. So, this implies that growth is not possible. Thermodynamically not possible. But if R is greater than R star, then delta GF decreases as R increases, which means growth is now possible. Growth is possible. So, which this clearly indicates that the new nucleus which forms has to have at least a minimum radius of R star, because anything less than that the growth is not possible. So, that is why we call this R star critical radius for nucleation. So, nuclei cannot be less than a critical size. This is a very, very interesting result, because recall that we are talking about a temperature T which is less than the freezing temperature. So, even if the liquid is below the freezing temperature, a solid of radius R less than R star cannot form. So, one has to assemble a solid ball of radius greater than R star for the growth to be possible. So, this is the critical radius for nucleation. We can find this in terms of our variables which we introduced. So, recall that we are saying that at R star delta GF is maximum. So, at R star delta GF is maximum, which means the differential coefficient of delta GF with R at R is equal to R star should be 0. So, if we start with our expression and differentiate it with respect to R, we can expect to find R star. So, let us do that. So, remember delta GF we wrote as sum of two terms, the volume term and a surface term. And to apply the condition for maximum, we differentiate this. If we differentiate this expression with respect to R, then we get 4 by 3 pi differential coefficient for R cube will be 3 R square minus GL 4 pi. For R square we have 2 R as its differential coefficient and gamma. So, we have 4 pi r square Gs minus Gl 8 pi r gamma. Now, we apply the condition for maximum. Which is del delta Gf by del r. R is equal to r is equal to r star. This is equal to 0. So, which means I substitute r star in this expression and set it to 0. So, I do that 4 pi r star square Gs minus Gl 8 pi r star gamma is equal to 0. So, you can see now we can cancel many terms, pi cancels, r star also cancels with the cancellation of a square here, and 4 cancels with 8 here too. So, we get an expression for r star as 2 gamma by Gs minus Gl with a minus sign, minus 2 gamma by Gs minus Gl. You recall that Gs minus Gl itself is negative. So, that is why we have a minus sign there. So, R star gives you a positive radius. Now, if you think about it, so this Gs minus Gl is the driving force. This is what is finally making the transformation possible. So, it coming in the denominator is justified in the sense that higher is the driving force, smaller is the critical radius. So, which means you have, if driving force is high, then nucleation is easier. You have to assemble a smaller number of atoms, you have to form a smaller critical radius for nucleation to happen. So, more the driving force, smaller is the radius. On the other hand, you can see that gamma is in the numerator. This gamma is actually an obstacle to nucleation. We saw that the surface energy term was making a positive contribution to delta Gf, which is thermodynamically not liked. If the transformation has to happen, you want to reduce the free energy and not increase the free energy, and 4 pi r square gamma was trying to increase the energy of the system. So, this is in a kind an obstacle to nucleation. Obstacle or barrier you can call. So, larger is this barrier, larger is R star. This is again understandable, because if more is the barrier, nucleation becomes difficult, and that is reflected in the fact that you have to assemble larger number of atoms now, make a larger radius of ball for nucleation to happen. We have recall that we had formulated an expression for this Gs minus Gl. So, Gs minus Gl, which we can call as delta Gv, and we had shown that this is nothing but delta H delta T by Tm, where delta T was T minus Tm. This was the undercooling. And I can write it as delta Hm. So, this is the latent heat of fusion. And this is the melting point. We had derived this expression in a previous video. So, if we use this, we can see how critical radius will depend upon temperature. We can write R star minus 2 gamma Gs minus Gl delta Gv delta Hm delta T Tm. So, this is another way of now seeing that of course, gamma will also vary with the temperature. For the moment, if we neglect the variation of gamma, then we can see higher is the undercooling, higher undercooling means lower temperature, will imply a smaller r. So, lower is the temperature of solidification, smaller is the critical radius.